All right, let's go ahead and get started today. First thing's important, exam 2. So that's coming up Monday, week before Thanksgiving, or the week of Thanksgiving, which is next week. So this exam will be similar to like the first exam, except this time you get to bring one piece of 8.5 by 11-inch piece of paper for notes, front and back, that you can use for this one. And the main reason is for doing that is we have lots and lots of concepts that you need to have kind of under your belt. So let's kind of go through the topic list. So this covers homeworks 5, 6, and 7. First off, changing sampling rate by non-integer factor. So that should ring a bell in terms of what happens when you downsample to the spectrum of a signal. What does that do to it? Or what happens when you inject zeros? So know those formulas or know those concepts. The block diagram for changing the sampling rate. What do you have to do? What is the cutoff for those filters that you're going to be using? So those block diagrams you need to have under your belt. The polyphase decomposition for upsampling and downsampling systems. So there's 2 block diagrams that were kind of general purpose block diagrams that would describe either case. So make sure you have those. The structures for signal processing, so that direct form 1, 2, and transposed form, and know what those are in the second order sections. And so if I ask put something in a parallel form, direct form 2, understand what that means. If you use a second order section, and so forth. Obviously, sometimes you might have to do partial fraction expansion, but that's no biggie because you already done that before, but may have to use it again. The next big concept was filtering, and so this time understanding the filter requirements, passband, stop band, transition, the gain of the filter. Obviously, you're going to be needing to know what kind of filter and cutoff you need when you use the upsampling and downsampling, so you need to have that sort of under control. Probably will still need the concept of the anti-aliasing filters. We talked a lot about that about the first test, but sometimes to build problems that describe these, we have to reuse that concept. So that's another thing that may be on this exam. And finally, the last few lectures, properties of the DFT, linear and circular convolution, block convolution. The properties are going to be on the sheet. I think I said here, any required tables will be provided, so you don't need to memorize any of those properties or waste space on your precious paper, since those will be provided. If you need a property, that will be on the exam and in the table. And we talked about how circular convolution can accomplish the goal of linear convolution. So make sure you have that under control. And I guess the last 2 lectures we talked about block convolution, the overlap add and overlap save. So that's, you can get questions on those. Obviously, you're probably not going to be able to work out an entire numerical example during the exam on that, but you may be asked to recite a recipe with what are the lengths of the sections, what are the overlap samples, and so forth. What would it look like if you were to implement a block convolution algorithm? So that's also fair game. And I guess finally, last time we started the decimation in time DFT, to kind of understand the general, the general principles of the decimation in time, which was the idea of taking the input sequence and dividing it into even and odd and kind of breaking it down. And as we went further into it yesterday, that it ends up with n log n operations for complex multiplies. And I guess the other thing was it really breaks an FFT into 2 smaller FFTs, and it keeps doing that over and over again. I think we played around with it in MATLAB, and you could see, yep, we just keep making smaller and smaller FFTs. And today we're going to finish up that topic and move into another algorithm called decimation and frequency. And that's not going to be on the exam. We're going to stop at decimation in time. But it is also another sort of a family of FFT flavored type algorithms. So let's see, no electronics, and if you're a distant student who wants to take it, make sure you take it on the same day, or give me a call or email. Any questions about the exam. And it'll be in this room. That's the other thing. We don't have a big room to play in on Monday, so guess we're here. All right, if that's all we have on that, let's try to finish up decimation and time and move on to decimation and frequency. So last time we spent a lot of time trying to understand how to make the FFT or the DFT more computationally efficient. We talked about FFTs are basically a family of algorithms, and one of the ones we're getting into in depth was decimation in time. And we kind of ended up with that showing, I guess, mostly heuristics. Didn't really do an in-depth proof of some of its computational properties. We kind of suggested them. Today we're going to show some structures that really make it more clear, some of its properties. So let's sort of revisit, I think, where we were last time. So we were doing a simple example, right, where we're doing a 4-point decimation in time algorithm. And we're going to take it step by step and just decompose it so you can see how the structure turns out, because that is really some of the key properties can't really be understood unless you see the flow diagram is what it comes down to. So we're going to kind of derive the flow diagram so you can see where that where those properties come from. That's the main thrust of today's lecture. So as we talked about last time, we can take x of k, break it into these other two, g of k and h of k, where I think we played around in MATLAB and said, oh, this is basically a 2-point DFT. So we can sum these two 2-point DFTs together and kind of have this glue term here, which kind of puts it back together and makes a 4-point DFT. So we're going to go through this and write down the equations in gory detail and see how they're implemented in a flow diagram. And that's we're doing it in a 4-point decimation in time, so it won't take us all day. But I think you'll get the major concept if we can break it down like this. So if we're going to do this, the first thing we've got to do is get g and h before we can implement equation 1. So let's go back to what these guys were. And luckily, they're only 2-point DFTs, right? So it's just the even samples for G. And that's in K. And K is just, what, 0 and 1. Pretty straightforward. So now we're going to break this up and actually run it. So if we have G of 0, what is that? Well, that makes K 0, so it's just a simple sum. So that's pretty straightforward. x0 plus x2. So we just sum those elements. But k can also be 1. So what does that leave us with? G of 1 is x of 0. N is 0, so just what we call twiddle factor, or phase goes away. It's also 0, but x2 now has what? K is 1 and n is 1, so we end up with just W2 there. So what we're going to do is do the same thing for H, and then we'll have basically 4 sets of equations to see how things are progressing. So let's revisit what H was. So H was also a 2-point DFT, but it was the odd samples. Right. So that's just the DFT formula for 2 samples. And luckily, it's very similar. Right, we can put H0, and that's going to be what? Just the sum. I think that's sum of the odd samples, right? So that'd be 1 plus x3, just like we had for G. And this one is going to be x1 plus x3 W2 again. So now if we've got these together, our next step is to go back to equation 1. And now we're going to put in the values for G and H and see what are the 4 outputs in terms of G and H. So let's call this equation 8. We'll make this the big bold X. So this is the DFT output of 0. And if we, maybe I'll do this so we can kind of see what we're working with. We're going to implement equation 1 now. So if K is 0, that's easy. G of 0, 0 modulo 2, 0. Not a problem. W4 to the K, well, that's just W4 to the 0, which is 1, so that's easy. So that just leaves us with H of, and K is 0, 0 modulo 2, 0. So that's our first equation for the output. Our second one, K 1 modulo 2 is just 1. And we've got 1 modulo 2 is also 1. And K is 1, so that's just W4. Now things are getting a little more interesting. So 2 modulo 2, well, in modulo 2 world, right, everything is 0 or 1. So we have to subtract 2. So 0 is what? 2 is really 0. Same thing for this guy. But now what do we have? This K was not modulo 2, right? So it's for 2. And our last output is 3 modulo 2 is just 1. Goes the same for H. We have W4, 3. So now what we're going to try to do is take these equations here that describe the output and our equations here that describe kind of the input, G0, G1, so these guys and these guys, that describe the inputs, X0, X2, X1, X3. Those are going to go into our system, become G0 and G1, or an H0 and H1 as well, and then they're going to get processed to become the outputs of the DFT. So let's try to put all this on one nice block diagram and kind of start from here. See if we can all start from the same place. So on this side we have our input sequence. And what we want to do is first off let's do the easy thing. We just sum X0 and X2. And that will give us G0. So if I do that, we're going to use our signal flow graph stuff from chapter 6. If I can make a triangle. So that's a sum there, and that gives us G0. And that's just using equation 3. So we'll shift that up. So we've got that part. What about G1? Well, G1 is also X0 plus X2, but X2 has a weight on it. So let's put that weight, which is W2. And this is G1. Now we've also got x1 and x3, and those should be down here at h0, so we can kind of shift everything up and work on equation 6 and 7 now. And say, well, let's work with equation 6, see if we can get it all on the page. So I want to add x1 and x3 together, just like I did for these two. And this should be h0. And finally, I want to add x1 and x3 together and get h1, and it has this weight w2. So let's do that on the bottom part here. So h3 had the weight. So now we've done what we're going to find out is kind of our first stage of processing. So that brings us to our other equations. And let's see if we can do these two first. See if we can get it all on the same page here. So we're going to try to implement equation 8 and 9. So what do we need? So we need G0 and H0. I've got those two right here. That'll be pretty easy to do. So let's sum those up. And a weight of 1. Then we can use G1 and H1. So that's this one and this one.
How are we adding x1 to x0 to get output at 0?
Let's see. How are we?
The line, is that representing like an adding effect?
These dots are where things are being added. And these triangles, which hopefully are legible, not really, but they're close, are weights.
But from this x0 output, we're going from the third line.
Oh, right here?
The x1.
Okay, down here, okay, right.
How are we going from adding from that line to x0 to get that output?
This is just breaking off, so this is H0 after we've added x3 to x1 is H0.
And we're just adding it to g of 0?
And then we're just adding H0 to G of 0.
Okay.
So it's just branching off and taking the value with it.
And is that the same as x of 0?
And it is not. This is the output. And so I'm trying to make these kind of like outputs of the DFT, big and bold. These are input. These are mostly, we'd like to think of them conventionally as time inputs over on the left and frequency samples on the right. And it's easier in the book because they always use capital X for the outputs. So now let's try to put together, let's see if I can make this big and bold so it doesn't look like it's a recursive system where x of 0 is out here, then it feeds back around magically, which I'm not showing you back in because it's not doing that. That's not what's happening here. So let's take let's start from here. See if we can move it up. And if we can get it all on the same screen, because it's hard to see what's happening. So x3, we said, was weighted, right? Or h1, sorry about that, is weighted by w4. And that was added to g1 to give us x1. And so carefully, we have that output now. So that leaves us with these last two. So let's look at them briefly. So this last frequency sample, or this x2 frequency sample, is G0 plus H0 with this weight of W4 squared. So that's what I'm going to try to put into our table here. G0 plus H0 W4 squared. There's our H0, and it needs a W4 squared weight. I'm going to put right there. And we also need G0 to add to it. Is that right? Yes. So we'll have to bring G0 down. And finally, our very last example. Get it on the screen. Get it on the screen. Let's go back to our equation. It's equation 11. So it's G1 plus a weighted version of H1.
I have a question.
Yes.
Can you move a little bit to equation number 9?
You betcha.
So it's G1 plus H1 W4. So we don't need G0. What is this?
Let's see, did I draw it to the wrong one? Let's see. I may have. Let's see, we want x2 should be
right.
g0 plus x2. So I think this is right. x2 should be g0 plus h0.
Oh.
Let's see, did I? At least that's what equation 10 is. You're looking at equation 9 though, g1 plus h1. So let's go back to that. g1, h1. I think that's right so far. It should look, when we're done, it needs to look pretty because it needs to look like that, where you have what we're going to call these butterflies like this. Otherwise, it's you can almost tell that you've drawn it wrong if you've if you have it neat, because you're like, okay, that doesn't look like a DFT butterfly or FFT butterfly. That looks like
Okay, I guess
something wrong.
what I did not understand is because why on the right side you wrote X1, X2.
Right, and it's easy to get, maybe the right and left probably should in the future maybe use a different color for the inputs and outputs, just so the equations, of course then all the equations will be different colors too, but at least it'd be easier to understand. So let's go back and look at x3. So it's h1 times w4 cubed. So coming out of here I've got h1, so I want to put a w4 cubed, and I've got to add that to G1, so I drew a line from G1 down here, and that weight is just 1. So this is the kind of the famous DFT butterfly diagrams, or FFT butterflies. And they call it butterflies obviously because of this nice looking pattern of the wings of the butterfly. But there's also several things that make this, I guess, more compelling. I think I had some confusing tables last time where I went through and tried to show you that yes, eventually it's n log n, because you can break it down, log 2 n that many times, and it just takes n multiplies. But if you look at our simple algebra that we went through here, and we put this table and we put this together to represent it, it's pretty simple because the first stage ends at G0, G1, H0, H1. Well, how many complex multiplies would it have taken? We can see that each one of these is a multiply, add. Now these happen to be 1 here, so they're somewhat reduced, but each one of these outputs requires a multiply and an add. And usually, I guess for the purposes of this class, I've been just neglecting the adds, saying let's just count the complex multiplies. And the complex adds, it turns out, are usually about the same number. And multiplies are what? Four adds and what? 4 multiplies and 2 adds for every complex one. So they're the thing that's really driving us here. So we have a 4-point DFT. We've got one complex, 4, or 1, 2, 3, 4. So we had 4 complex multiplies. That's the first stage. The second stage is right here. It ends, right? There's only 2 stages. Why is that? Well, according to the theory, log 2, 4 is the number of stages, which I'm talking about is only 2. So we could break this down, this DFT down twice, and that was kind of the n, right? As we talked about last time, log 2n was the number of stages. And how many multiplies did it take? Well, there's n of them because there's this many stages and that many multiplies per stage. And that's why this is a little more compelling, because you can count the stages and count the multiplies. Stage 1, stage 2, 1, 2, 3, 4, 1, 2, 3, 4. So we're getting 4 complex multiplies per stage. We're getting 2 stages. And it's a little bit easier to see that way than some of the other ways. Now I think as we get a little farther, there's other things we can do to make it even slightly more efficient. But I think this is the big idea. Now the second thing to realize is look at the inputs. They're not in the order that you normally have them on hand. You know, if you have an ADD converter, it's sampling inputs, it's sampling them as you get them, right? You don't necessarily receive x0, x2, x1. No, you get x0, x1, x2, x3. So the addressing and setting up this data may not be perfectly the way you'd want it. And finally, the outputs here of the DFT are in the right order. So I think we'll go talk a little bit more about this structure in the slides here. So let's go to the slides here. All right. So this is a 2-point DFT, and it's obviously the butterfly shape. And one thing about it is the first output is basically just a sum. And so sometimes that's called the DC bin, direct current. It's low frequency content. Unlike this bin right here, which is bin 1, it's the difference between the two. So it has all the high frequency information. And of course, the shape gave rise to a butterfly, the name butterfly. So let's look at the 8-point decomposition. So this gives you the full decimation in time 8-point. And we're going to look at this one a little bit just to take it up a notch so you can kind of see that the 4.1 shows you some things, and the 8.1 I think kind of hits the concept home. So when we look at this, we can see now that there are 3 stages, which makes sense. Right? Log 2 of 8 is 3. So we've got the 3 stages. We broke it down 3 different times. And so that each stage is going to require, 1, 2, 3, 4, 5, 6, 7, 8, 8 complex multiplies to get the outputs for each stage. So hopefully it's kind of clear that, yeah, it's going to be n log n, or in our case, 8 times 3. Let's see. Now we can make some, there's some clever things we can do to try to make this a little bit better. So here's the first one. Many of those butterflies in the last example, let's just pull up this one, kind of had a form like WN0, or you can see WN4, WN6. I think some of these are. It uses, WN2, WN6. I think you can see that there's the difference between them is this value n over 2, which for us was 4 in the last chart. Well, if you can do that, if you have a situation like this, you can factor out this weight, Wn bar, which doesn't seem like it does you much good until you recognize we're just exploiting the periodicity of that complex weight. So instead of a multiply now, we can just do a subtraction because the weight becomes -1. Well, that eliminates basically a complex multiply from every stage. So now instead of n log n, it's n over 2 log n, which is, it's not nothing to have that extra savings. So if we go ahead and, do that, we can, I think, get it. Let's see. We can get it to look like this, right? I want to make sure we're on the right slide. So all these complex weights on the bottom now became -1s. It really simplified it. Now let's see. What I wanted to talk about next are some of the nomenclature here. So each one of these WNs is sometimes called either a complex weight or a twiddle factor. That's kind of a historical term because it was twiddling or adjusting the outputs. And so all those adjustments were supposed to add up to the final DFT value. And one of the important things about this architecture is not only the fact is it efficient in terms of number of computations, but one of the amazing things is it's also efficient in terms of the memory required to execute it. And that efficiency is called in-place computations. We'll try to get into that a little bit more on the next slide. But what that means is when I go from, let's say, the first stage to the second stage, if someone gave me this diagram and told me I was going to do this, naively, I would create an array to hold the input data, and then the same array to hold the output, and then just, type up, okay, multiply this times that, and then I have my two copies. Two copies of the input data and the output data. So I guess I have two arrays. Well, it turns out that you don't need two arrays to do it this way. You don't need a full copy of, this data here and this data there. You can just use one copy and maybe a little bit of scratch memory to go back and forth. So that's efficient. So it doesn't seem like much when you're looking at an 8-point DFT, but if you have a million point FFT or something, then it starts to become more significant. So let me just try to walk you through an explanation of how that might work. So we have our DFT butterfly here. We have some input data, x0, x1. And we're going to try to implement this thing and get out x0, x1. And I'm calling them the same thing because they're places in memory. So you can treat them what you want. You can think of it as time. You can think of it as intermediate result. You can think of it as the final result. You can think of it as whatever you want. But it's in some kind of firmware or on a processor memory. So it's just sort of sitting there in memory. So to implement this, we could have, this is just 2 places in memory, but this could be, it could be an array of thousands of elements, right? Well, the first step, before we even get started, is to save this product in the scratch memory. So we're going to save whatever's in x1 times this weight. So we have our element, we have our array, and a register with some value in it. Well, we're going to go back to x1, and what we're going to do is just take x0 minus scratch. What was scratch? Scratch was the original value of x1 times WNR. So the neat trick is that we didn't have to make another copy. We could just overwrite what was in x1 with this new value. And so when we could do that, then we take what's in scratch, add it to x0, and overwrite the value of x0, and we're done. And so all I did was use some little scratch memory or register, which then could be run over that entire array one at a time and done all 10 million calculations. I didn't need 2 copies. So for us nowadays, that's only something of value or interest when we have enormous FFTs. But in the old days when they were originally designing this stuff, it was a pretty nice capability to have. So let's see. Now I think I wanted to talk about the.
So whatever was x1, then put it to x0.
We were taking. Let's go back. So what was in x1 was just some, I guess, the original data value. Then we multiplied it times this complex weight and put it in our register or scratch memory.
Right.
The next step was we overwrote the original value in x1. It's gone forever now. Who knows what it was? With what's in x0, the element above it, minus what's in the scratch memory. So now this is gone forever. We overwrote it with this.
Is that the value of x1 times the weighted, the original x1 times the weighted value?
What's in the register?
Yeah, what's in x1 right now?
What's in x1 right now? At this point, it's just the data. Then we go to the next step, which is we overwrite it with x0, which is this value here, minus what's in scratch. And scratch was the original value of x1 times the complex weight. So we're just trying to do this. We're just trying to follow the formula on the screen, I guess, in terms of the flow graph. So I hope it's x0. It comes down here, and this is x1 times the complex weight minus 1, which is this formula right here. So I'm trying to execute. And the key is we just overwrote the original value of the data of x1. It's gone forever. But the key was we don't need it anymore either. The only thing we do need is this in scratch memory, and that's for the next step when we overwrite what's in x0, and it's gone forever. Right. So think the next step was, let's see, that's 11, 10, 9. So I guess the other thing that in-place computations that we have here is that you'll notice, and it's just kind of like a pattern. Notice the architecture is the inputs and outputs are kind of horizontally adjacent from each other. So it's obvious up here in the first stage where it's like, wow, these things just sort of swapped. But input, output, input, output. If we go to this one, there's an input, output, input, output. And you can see that this one at the top comes down. And so they kind of interfere with one another, but it's really just the same pattern over and over again. And when you see that adjacent inputs and outputs, that means you can kind of jump to the conclusion, and I think it's almost, I think it's correct, is that it's an in-place computation. You can get away with saving a lot of memory. Now, if you look through the book, I think they show you some examples of things that you cannot do. You cannot do with in-place computations. And so I think there's some flow diagrams they have in there where the inputs are in normal order and the outputs are in normal order. But if you do it that way, you can't use in-place computations. Excuse me, sorry about that. So what is this bizarre shuffled order? The 0, 4, 2, 6, 1, 5, 3, 7. That's called bit reversed order. And it results from the fact, I guess it's sort of a key that when you have that bit reversed order, it enables us to do these in-place computations, is the relationship. But how do we get bit reversed order? Well, the book has this diagram which I think is somewhat illustrates the issue. So if you have X, it's some data, and N2, N1, N0 are just bits that are part of the index. And so imagine it has a 3-digit bit representation of an index value. So since it's 3 bits, well, the index can only be 0 through 7, because that's what you can represent with a 3-digit binary number. So let's sort, is what they're going to do, based on the most significant bit, then the next, and then the next. So that's why they put this N2 here, 0, 1, and sort based on the second digit, 0, 1, and then based on the third, 0, 1. Well, when you do that, 0, 0, 0 gives you that index. 0, 0, 1 gives you this index. And you look at it, it's just 1, 2, 3, 4, 5, 6, 7, just what you'd expect. And so nothing new there. But suppose now that instead of sorting based on N2 first, the most significant bit, you sorted on the least significant bit. Hence bit reversed ordering, or they could call it, least significant bit sorting, or, you make up the term. But if you turned it around and said, oh, instead of my number is N2, N1, N0, but I'm going to sort on N0 first, N1, and then N2. Well, if you do that, then you end up with this bizarre ordering. Which is what, 0, 4, 2, 6,
Is that like
1.
Exodus almost? Or a binary? Or is that just application?
Yeah, I think it's just the way you treat the binary number. In some sense, if you just reverse the binary number, right, I think if you turned all these around, you get the same thing. So you don't have to think of it as a sorting exercise. You could think of just writing it. In fact, if you're a computer architecture person, there might be a big Indian, little Indian treatment lurking in here. It's like all of a sudden I got bit reversed order when I used the wrong ordering of the bits. So that's what we end up with. Okay, decimation and frequency. So I think that ends our discussion of decimation and time. That brings us to our last topic, where we're going to do a sketch of decimation and frequency. And where were we on that? So our last topic of efficient computation of DFT is just going to be decimation and frequency. So originally the decimation in time was like, okay, let's take smaller subsequences of the input sequence, X of n. How do we do that? Well, we started with the obvious. How about even and odd? That's the first way to break it down. And we kind of did that and ran that through. But someone might say, well, since X of n and Xk really are kind of the same data, I mean, right? They're one-to-one mapping in some sense. It's it's just samples of the DTFT. So isn't one as good as the other? So instead of taking samples of X of n, what if we just took samples of X of k and broke that down? Why privilege the time samples? So, with treating everybody equal in mind, let's go ahead and take the even samples of the DFT and the odd samples of the DFT, see if we can calculate those and break those down into simpler and simpler methods. So that's kind of how this is approached. Instead of even samples of the input, now it's going to be even and odd samples of the output. And one reason to cover this, I think, is because it helps remind us of some of the tricks of using the DFT. And so let's begin. So we remember one of the important things was that this discrete Fourier series, which I'm putting the tilde over it to remind us we're talking about discrete Fourier series, which is really just, right, it's really just a periodic version of the DFT outputs, right? And we just agree to refer to it that way. We pretend that the DFT and the discrete Fourier series may be different things when we know one of them is a periodic extension. So when we did this, we went through some fun math to show that why this is a discrete Fourier series of the original value of X of n, that's R. And so the nice thing was if we had samples of the discrete time Fourier transform of it, and we took n samples, we could recreate a sequence that was n. And if n happened to be, or if x happened to be smaller or equal to n, then it was perfectly reconstructed and there wasn't any aliasing. Everything was fine. So what we're going to do is think, well, what sequence could we construct so that all we get out when we do the DFT is the even samples of the discrete Fourier transform. So how can we mess with X of n so that if we do a DFT, we just get the even samples? Well, first off, you know that we're going to do something to X of n to make it half the length, right? So something's happening there. So I guess the first thing is to just blindly go with the formula. Let's see what happens that I just wrote here. Let's take this and say, I'm only going to do n over 2, divided by n over 2. So I'm only going to do n over 2 of those samples, 2 pi k divided by n over 2. So when we just plug and chug over here, what falls out? N minus R, but this n and this n are related, obviously. There's what drives the whole thing. So now we end up with this. So to kind of unpack the essence of this, let's do another kind of simple example where we write it down and just see what this looks like. So since there's an infinite number of r's, I usually like to be selective and look at r equals 0, r equal minus 1, r equal plus 1, and say, okay, we know it's going to be periodic, like it always is, but let's look at these first and see if we can understand the pattern, right? So first off, let's let r equal 0. Let's see if we can get our arms around this. So if r is 0, and this is just the sum, of all these different ones, but we're going to write down just the r equals 0 case of x of n minus, well, r is 0, so it's just x of n, right? So this has value x0, x1, x2, and we're getting tired, so let's jump all the way up to xn over 2 minus 1. The next one is going to be what? X of n over 2, and dot dot dot. Let's keep going to the end. And I'll just draw an arrow and say that is x of n minus 1. This is 0, 1, 2, 3, and this, whoop, that's not 3, that's n over 2 minus 1, n over 2. And this n is, of course, n minus 1 there in that index. So maybe it's not completely clear, but every one of these indexes here is up here in this box. X of 0 is 0, x of 1 is 1, x of 2 is 2, x of n over 2 minus 1 is at the index n over 2 minus 1. So far so good. Now, let's let r equal minus 1. And take a look at what happens with our formula. So now we've got x of n minus a minus is a plus, plus n over 2. So what's that going to end up doing? Well, that means when n is 0, we've got x of capital N over 2. Right? So that's the way to start first. That's n over 2 now. Because just the brute arithmetic of n minus a negative minus a minus times n over 2. So that's x of n plus n over 2. So that's at 0, this is at 1. That's going to be n over 2 plus 1. And let's pull that up a little bit. And let's go all the way out to n over 2 minus 1. So that's going to be, the n over 2 minus 1 is n, which is going to be right here, plus n over 2. So that'll be at n minus 1. It also might be interesting to say, well, what happens at n over 2? Well, it's going to be n over 2 plus n over 2, which is just n, but there's nothing at x of n, right? It only exists from 0 to n minus 1. Now, of course, we could say, well, what about minus 1? Let's make sure we got our bases covered here. Well, that's going to be x of n over 2 minus 1. Right, and we can keep going. There'll be obviously some terms all the way back till we get to what this is minus n over 2. Maybe we'll get to x of 0. I think that's right. So let's look at our final case, which is let r equal plus 1. So if we do that, let's get back to this. This is going to be x of n minus, that's a plus 1, n over 2. So that's going to shift everything to the right. So how do we draw that? That means we start at n over 2. And that's going to be x of 0. So that's n over 2 plus 1. That's x of 1 dot dot dot. Things keep moving. So what happens if we just sum these things up? If we look in this area right here to n over 2 minus 1, we end up with x0 plus xn over 2, x1 plus xn over 2 plus 1, etc. So what has this done? It has done two things. First of all, it sort of folded the sequence back on itself, and it's made it periodic with period n over 2, which it has to do. And you can kind of see that if you look at our diagram here, because it starts at x0 plus xn over 2. Well, if you look way out here, when it starts a new sequence, there's x0, there's xn over 2, right? And they're starting at n over 2. So the sequence is periodic from 0 to n over 2 minus 1. So let's try to summarize what happened in the pictures. So first of all, reconstructed sequence is periodic. With period n over 2. So that's good because we took n over 2 samples of x, e, j, omega and then reconstructed it, so we had to have a periodic sequence with period n over 2. So another way of just saying that is outside 0 n over 2 minus 1, there are copies, right? So if we carefully look at this, I think, how do I want to do this? The even samples, xk, and this is what? These are the samples, 2 pi k all over n over 2, samples of a DTFT, are what? X of n plus x of n over 2. So we kind of folded the sequence back on top of itself. For that region. So if we wanted to use the DTFT, or use the DFT, sorry, to implement it, we could say, okay, x even of k is just the n over 2 minus n over 2 samples of the somewhat peculiar sequence. And sometimes this is referred to as data turning, because under in some applications, some people found that they can get almost the same performance in their particular application with a with an FFT half the size, because they can just fold the data on itself and take a smaller FFT and still do what they need to do. And that's all over and over 2. And I'm trying to make this neat because this is going to be kind of a boxed formula here, because we're going to revisit this later. So now with this in mind, all right, we can take the data sequence, we can kind of fold it on itself, make an n over 2 length sequence, and just do a n over 2 point DFT. That gives you the even samples of the full point DFT. So that begs the question, of course, well, all right, that was cute, but it's only half the answer, right? We got to do the rest. So what about the odd samples? So the odd samples we can get if we just basically do the same thing all over again, except shift the thing. So let's revisit one of the shift properties. and then we'll bake that into our derivation of the other one, and you'll see that we can get there pretty quickly. So this was table 8.2, on page 660 in the book, property number 6. We can basically multiply the input sequence by this complex modulator, really is what it is, and we end up basically circularly shifting the output DFT. And to me, this is it's almost like if you've taken any RF classes, it's basically just the same as, up converting a signal or down converting a signal. You're shifting it in frequency by multiplying it times. Even though this is hidden, this is really just an exponential. It's a complex exponential, which is a cosine plus a sine with some frequency, and you're multiplying it, so you're modulating it. You're shifting it in frequency. So it's kind of hidden, but it's obvious and something you already probably knew. But it's just hidden in this complex weight nomenclature. So what do we want to do? Well, to shift x of k to x of k plus 1, we'll let L equal minus 1. So if we feed that in, that tells us what? Wn to the n, x of n, is going to give us k plus 1 modulo n. And the good news is this Wn, which is a reminder, 2 pi n over cap n. So let's kind of put it all together. Because what we want is the sequence whose DFT is that 2k plus 1, right? So the goal, maybe I'll put goal, x of 2k plus 1, or k equals 0, 1, dot, 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 n over 2 minus 1. That's what we want. Well, let's attack it kind of in 2 steps. We know how to get the 2k part. We just did that. Right? So that's the x of n plus n over 2. That will give us that part. But now what we need to do is shift it. So let's multiply x of n, and we need to shift it by the weight, because shifting it by 1, put it there. This one is n plus n over 2. Also needs to be shifted by 1, so that's going to be Wn. But notice, since this index is n plus n over 2, this also needs to be n plus n over 2. So I'm going to carefully put that there. So that's the part that you might have missed. This x of n and this n have to be the same for it to work. So to shift this one by 1 was pretty easy. To do this one by 1, you have to include that x of n plus n over 2. If we do that, then we can get, call this a DFT relationship to 2k plus 1. Now the first thing that might be interesting to look at is, well, this complex weight is a little bit complicated. Can it be simplified? So let's look at that. That's the same as n, Wn n over 2. And what's Wn n over 2? It's e to the minus j 2 pi times n over 2 divided by n, right? Well, the n's cancel. 2 cancels, that's e to the minus j pi. So that's just a fancy way of writing -1. So we can end up with that, which is really nice because that's just a negative of the weight we have there. All right, so we can make this look real slick when we put it into our formula. Because now instead of adding the 2 like we did to get the even, we're going to subtract the 2 and then tack on a weight and take the DFT, and we're there. We get the odd samples. So it's almost a cute little symmetry that pops out. So if that's the case, let's go back to x of n, and I want to write it carefully. And we'll do it in 2 steps so you can kind of see what happened. That's n plus n over 2. So we said that is the same as minus x of n plus n over 2 through the simplification. Now we can finally write it as x odd. The odd parts are going to be n equals 0, n over 2 minus 1. Now we can put this x of n minus x of n plus n over 2, and the whole thing times w cap n of n raised to the n. And now we have to take the DFT, so that's e to the minus j 2 pi nk all over n over 2. And that gets us the odd parts. So now for our next step is we're going to kind of do what we did for the decimation in time. We're going to start with a 4-point example. We're just going to crank out the x odd and the x even parts of the DFT, and then we'll make a flow diagram, and then you'll see the relationship between the decimation frequency and decimation in time DFTs. So that's where we're headed. So let me make sure I can find the even one because we'll need it. So with that in hand, let's do decimation and frequency n equals 4. And let's start with the even. So I'll put this sort of in the toolbar here of the blue pad area. So we've got our formula. And what we want to do is just crank out the formulas for each one of these. So if we put in k equals 0 here, we end up with summing this up, right? Which is, that k is going to be 0, so this whole factor goes away to 1. And so when n equals 0, we have x of 0 plus x of n over 2. But what's n? N is 4, so that's 0. 4 divided by 2 is 2. So we end up with that. I'm going to put it in parentheses because it's shadowing the parentheses in this formula, because that was the first term when n equals 0. But now n's got to equal 1, so we have to redo it. X is 1. Now n is 1, and n over 2 is 2, so that's x of 3. Now n is 1, but k is still 0, so that twiddle factor goes away. We end up with just a sum. And that's something you probably already knew, because when you take a DFT, the 0 bin is always the sum of all the data, right? So it had better worked out that way, or something's amiss. So let's look at our next example, our next output. So here's our even sample here. So if k is 1, doesn't really matter yet because n equals 0 and equals 0 there. So we have the same thing in the top and the bottom so far. But now what about the twiddle factor? K is 1, but n is 0. So if this n goes to 0, that's gone. So we have x of 1 plus x of 3 again. N is 1. K is 1. Oh, now we have something left over. So we've got this whole e minus j 2 pi 1 times 1 n over 2. N is 4, so 4 divided by 2 is 2. There's our complex weight. This is a 2-point DFT, right? Because we started with a 4-point and we're getting the even and odds. Well, there are only 2 even samples, so we're done. So let's go to the 0th of the odd. So let's toss this guy and put this one in our little toolbar area if I can. I don't know if I can do that. I like the idea of doing it. So let's take a look at the first sample, which is the 0th. N is 0, so that's easy. 0 minus n over 2. N is 4, so we've got that. N is 0, that goes away. N is 0. This extra twiddle factor goes away. So we got to keep track of 2 complex exponentials now. This one and that one. But luckily with n 0, it gets rid of them both. And with k 0, same thing, right? So that goes away, and we end up with, I'm saying x of 1 minus x of 3. N is 1 now, so we end up with something here. And this is what? It's capital N, so it's 4, and n is 1. So we still end up with a complex weight there. Now let's get the last one. So the very last one is n is 0. And k is 1. There's no factor there. That goes away. And that leaves what? K is 1, but n is 0, so that goes away. So I think we're just left with that. Now let's be careful here because I think we've got more trouble. So when x is 1, n is 1, n is 3, we've got that. So n1 plus 2 is 3. All right, I'm catching up now. N is equal to 1, so we've got that complex weight. And then we've also got n and k both equal to 1. So we have another complex weight over here, and I think I'll just write that as that to save space. But that's basically the e to the minus j 2 pi all over cap n over 2. You said n is 4, so it's over 2, hence this 2 there. So a little bit complicated, but very doable. Now let's map these using the boldface font. So these are the proper outputs of the 4-point DFT. And so that's going to be equal to what? The 0th output is the 0th output of the even. This first output is the 0th output of the odd. It's the first odd. Two is going to be the first there, and our last output is here. And I do this because we're going to try to build kind of the flow of all this. So I need this and this. So now what we're going to do is basically take, let me see if I can get it all on screen. We know this, so we know what the outputs need to be. So we can map outputs that we care about to these intermediate quantities, x even and x odd. And we can map x even and x odd, 0 and 1, indexed into what? All the stuff that's now currently on screen, which are what? Functions of the input variables, functions of the input sequence. So now it's a simple matter of lining up these input sequences and doing the same thing. So we only have, what, 4 equations basically to put into the table or put into that structure. So let's try it. And we'll start with, let's start with this one. So to get x even, let's see if we can put it on screen all at once. I think what I'll do is I'll put the inputs in normal order, x0, x1, x2, x3, kind of to start with. And this creates some lanes here. And what do we want to get? Well, we know we need x0 plus x2 is something we're going to need. So let's get that. And we also know that, and so this, we also know that we're going to need, where did it go? For this x odd 0, we're going to need x0 minus x2. So at some point, we're going to need that. So I'm going to create that right there. So that's x0 minus x2, x0 plus x2. Now I think the next one we want to look at is, how about x1 plus x3? So we end up using that for this one, and we're going to end up adding that to get x even of 0. So let's get that, x1 plus x3. And we've captured that one, x1 plus x3. And we need x1 minus x3 as well. So let's put that here. Now some of this may be a little bit mysterious. Like, how did you know to put them where you put them? But I'm doing it more like for a reason, because you're going to see how these two things are related. It's more of a, it can be related as opposed to it's clearly, obviously related. And so for our final outputs, let's look at x0 even. And we know this x0 even, it's hard to show that because x0 even is also x0 of the entire DFT output that we care about. So this was the input, and this is output. And I'll use the bold font here to try to show that x0 even is not only this output, but it's also the output we care about. It's the 0th bin. It's the DC bin. It's the bin we want. And as we showed, it is the sum of everything. So if we want that, we're going to have to sum that up to get x even. Now if we look at a related one, x even and this is the second one out. So you kind of see what I'm doing now is the outputs are x even 0, 1, and that's going to be x odd 0, 1. So let's go back to x even 1. And you can see that it's x0 plus x2, which we've got up on top, plus x1 plus x3 times w2. So I've got to be able to take this and apply a weight to it. And I don't have much room to do that, do I? W2. And this is odd. It should be odd 0, and this is odd 1. Need a bigger pad so we can show each one of these is really corresponds to an output of the DFT as well that we care about. So let me just fill in the rest of it. W4. And this is 1. And this weight here is W41, W21. Wow, that's not as pretty as I wanted it to be. But the key point is that you can take those formulas that are algebraic and just kind of like the decimation in time 4-point value and create a butterfly diagram just like this where you have in-place computations. But there is a special kind of a relationship between these guys, and you can tell that if we swap these two rows here, you'll get basically the same flow graph. So let's try that on this page here. So let's see if we flip these two. Now instead of going twice as far down, x2 is now close to x0. So that's what I'm going to try to put together here so you can kind of see how it all flows. So we've got x0, x2, because we flipped it, x1, and x3. Now these guys are almost co-located. This makes drawing this a little bit easier. And so before, we had these going across, now they're closer together. Of course, when you do that, these got closer together, but now the next stage got further apart. And that skips that one, and let's put this is W2 of 1. And I think our final outputs here are like so. W4, W2, and then our final W4 here. Now I swapped this, so this is odd of 0, x even of 1, and finally x should be x odd of 1, and it is. Now what I wanted to show is if we go back, kind of in the Wayback Machine, to at the very beginning of the lecture where we were messing with decimation in time, we ended up with a flow graph like this. This was the decimation in time flow graph with the butterflies, and the two double wide butterflies, if you would. And we ended up with basically the same thing for the decimation in frequency. So it kind of begs a few questions, like why bother having a decimation in time and a decimation in frequency if they apparently have the same complex number of operations and they apparently do the same thing? Well, the only advantages or if you look at the inputs and outputs, how they're arranged. So let's try to summarize. So for the decimation in frequency and decimation in time, the butterfly operations are transposes. So if you go through the fancy flow graph reversal and transposition, multiple input, multiple output versions of that, you can go from one to the other without any changes. The other key is both allow in-place computations, which is a good thing.
You said end place?
It should be in-place computations. Did I? Yeah, in-place computations. You don't need any more memory. You don't need to make double copies of everything.
I think it's not showing anymore.
Oh, are we out of time? Oh, wow, we're way past time. Sorry, guys. Trying to finish up and just lost the fox on time. That's what happens. Hope we can get it done.
I need some more time to watch this. I really like that. Wrote a lot.